In today's video, I would like to introduce a very nice problem regarding arithmetic and number theory. Here is the following setup. Our goal, we are going to find the smallest primes p and q, which is for finding this following equation. Okay, we have q squared minus 2 times q equals p cubed minus 5 is multiplied by p squared minus 8p minus number 3. Okay, by the way, don't forget to hit the subscribe button and support the channel. Now let's jump into the solution. So let's move this minus number 1 to the left to make the quantity square at the left hand side of this equation. So we get the following. We get q minus number 1 quantity square. As I moved number 1 to the left, I get here quantity square. For the right hand side of this equation, I get p cubed. I'm going to split this term into two pieces, and as well as this one. Okay, minus number 2, because I already moved minus 1 to the left, I mirror this quantity square here. So if you take a look at these three terms here, almost are the same. Okay, just we need to take number, we need just to take p here as a common multiplier here. So we get here p factor p square minus 6p minus number 2 plus p square minus 6p minus number 2. Now it's more clear. We get a common factor here, this one and this one. Now we need to take it as a common factor here. So we get here, we get q minus 1 quantity square, which equals p plus number 1 factor p square minus 6p minus number 2. Okay, here is a nice expression here. We get a perfect square on the left hand side of this equation. We get a product on the right hand side of this equation. Okay, now we have done with the first step because we have factorized this one on this form. So what we need, time here, we don't need to make the comparison between p and q. Okay, we don't care about that. We don't care even about the more solutions. Okay, what we care about, we care just the smallest values p and q. You may have more solutions coming up, you may have no solutions. Okay, but it's very hard to deal with this equation with other solutions if you have a solutions. But the question, just you are going to determine the smallest values for these primes p and q. Okay, so we don't need to do anything here. So the only issue with this equation, because we have all primes are unknown here, so it's hard to deal with this equation. So what's the best way to work with this equation? We need to determine the GCD of this equation. Okay, how are we gonna deal with this equation for this product? Let's call this one as a capital A. Now we need to check the GCD of p plus number 1 and capital A. What's the GCD? Okay, now in order to check the GCD, I'm going to make a nice trick here in order to determine the GCD of this one. So if I'm going to add the multiple of p plus number 1 on both sides, the GCD is not going to be changed. Okay, so let's do that. So we get capital A, which equals p squared minus 6p minus 2. If I'm going to add or subtract the multiple of p plus number 1 on both sides, the GCD is not going to be changed. Okay, let's do that. Let's do the minus p factor p plus number 1. So what I have done, just I'm subtracting minus p factor p plus number 1 on both sides. The GCD is going to be the same. Okay, so now I'm going to simplify this one. P square is going to be cancelled out because we have p square here minus p square here, we have p square here. So I will be left with minus 6p minus p, which is minus 7p minus number 2. Okay, we get p plus number 1 minus p plus number 1. Okay, I need to get rid of this p as well. So by adding 7p, by adding the multiple of this one on both sides as well. So let's do plus 7 p plus number 1 on both sides. Okay, so adding this 7 p plus number 1. So for here, I get this 7p cancelled out because one is positive, the other one is negative. I will have minus 2 plus 7, which is 5. So I get 5 here. So this one become p plus number 1. I'm going to take p plus number 1 as a common factor here. So this one is going to give us number 1 here, minus p plus 7, which equals p plus number 1 factor 8 minus p. Okay. So what we find here, we found GCD of this p plus number 1 of capital A. Since we have 5 is a prime, which means that GCD is going to be equals number 1 or 5. Okay. Now we need to go through two cases. We don't know which one is a perfect one. Okay. We are going to go through two cases in order to determine exactly the GCD of this one is 1 or 5. Okay. Now let's get rid of this one and move on to the next step. Now first of all, we are going to check. We may have this one equals number 1 as a GCD. If we find it's impossible to be a number 1, which means the other one is a right one, okay, which is number 5. P or Q. You guys, you can check P and Q cannot be number 2 as an even prime, which means P and Q are odd primes, okay. So since this one is a perfect square, which means every term here is a perfect square. P plus number 1 is a perfect square. This one is a perfect square. So which means P plus number 1 is going to be written on the form of x squared, because we get GCD number 1 here. You will, this one is divisible by number 1, this one is divisible by number 1, okay. So both of them are perfect square. I get also p squared minus 6p minus 2 equals y squared. Let's do some motivation here. I'm going to subtract minus 5 on both sides here. What to do here? I'm going to subtract minus 5 on both sides. So I get here x squared minus 5, which equals p minus 4. Let's square both sides. So I'm going to do that. I get p squared minus 8p plus 16. The reason I'm doing this one, because I have a second equation is going to be written on the same degree as a polynomial, okay. That's why I have to square both sides. Now this is a good time to make a comparison between this one and this one, okay. But this one, when this one becomes smaller than this one, if we have p is super equal to 11 as a prime, this one becomes smaller than y squared, this one, okay. This is the only condition we have. This one is smaller than y squared, okay. If we have p super equal to 11, if we get p equals 7 or 3, it's impossible this one will be smaller than this one. Now also when we have this one is bigger than this one, okay. Also let's work on the other side. Let's subtract minus 4 on both sides now, okay. So we get here x squared minus 4 quadrant square. So as subtraction minus number 4 on both sides, I get x squared p minus 3 quadrant square. Let's do the same thing as I did previously. By distributing this one out, I get p squared minus 6p plus 9. Now if you want to make the comparison between this one and this one, we get almost the same thing. We get p squared here, we get p squared minus 6p minus 6p. The only difference this one and this one. This one is strictly this one bigger than y squared, okay. What do we have? We have this one, we have this term is smaller than y squared. We have this term is bigger than y squared. What we can conclude from this one? So we get x squared minus number 5 quadrant squared is smaller than y squared. At the same time, y squared is smaller than this one. X squared minus number 4 quadrant squared. What do we get here? So we have ended with this nice expression. We get a perfect square between two consecutive squares, okay. It's impossible to have a perfect square between two consecutive squares, okay. This is a contradiction. It's impossible. What we have contradicted? We have contradicted the GCD. The GCD of this one is it cannot be number 1, which is number 5. But remember, we have these conditions only when we have p is super equal to 11. You guys, you can check also p equals 3 and p equals 5 won't work, okay. Because if you check them in this product, is going to give us a negative solution here. We get a negative number which equals a perfect square, which is impossible. Okay, so putting this one and this one together with the same contradiction, which means GCD it cannot be number 1, it is number 5. Let's change number 1 with number 5 here. So the GCD of this one equals number 5. Now let's get rid of this stuff and move on to the next step. GCD of this one equals 5, which means this one is a perfect square, this one is a perfect square, which means the 5 is a multiple, which means this one is a multiple of 5. This one is also a multiple of 5, but 5, which means you are going to extract number 5 from here and also number 5 here. Putting 5 together, 5 with 5 is going to give us 5 square. Okay, so now we get this one is a perfect square. We get p plus number 1 as a perfect square. We get p plus number 1 as a perfect square, which equals 5 is multiplied by x square. Okay, also this one p square minus 6p minus number 2 equals 5y square. Okay, to find out the smallest prime p and q, I'm simply going to check the smallest values of x in order to find the smallest value of p. Okay, if I'm going to check x equals 1, it's going to give us p plus number 1, which equals 5, which means p equals 4. This is, it's impossible because p is a prime. Don't forget x and y must be a natural number. Okay, so checking the next case, x equals 2 is going to give us p plus number 1, which equals 5 is multiplied by 2 square, which equals 20, which means p equals 19. 20 minus number 1. Okay, now we have determined the smallest value, p equals 19. Let's check q. Just simply replacing this 19 into this one in order to find this one. Okay, so we get q minus number 1 quadratic square, which equals 20, because 19 plus number 1. This one is going to give us 19 square minus 6 is multiplied by 19 minus number 2. So calculating these things is going to give us 70 square. Okay, so taking the square root on both sides, of course we get plus sign because q is a positive here, so it's going to give us q minus number 1 equals 70. In the other word, q equals 71. Also we get a second prime. Okay, q equals 71 and p equals 19 are the smallest primes for this equation. Okay, so we are clearly done with this problem. By the way, don't forget to hit the subscribe button and support the channel, and thank you for watching. We will see you next video. Bye.